The area of a window is 4 times 4 meter. It means the area is 16 meter square and 5 centimeter square gap for thermal expansion. So let's say this is the window and the dotted line represents this area is 5 centimeter square. So del A is equals to 5 centimeter square or 5 times 10 to the power minus 4 meter square. We have to calculate the temperature difference that would fully utilize the gap. It means there was some certain temperature, and when the temperature is increased, this area, this solid area, will expand it up to this much, and this much as well. It means fully utilize the gap. So this is actually the gaps. Anyways, in this question, one important fact is missing, that is actually the linear expansion coefficient of glass. So let's consider the linear expansion coefficient of glass alpha is equals to 9 into 10 to the power minus 6 per coulomb. This fact have to be given in the question, somehow missed here. To solve this problem, we have to have the equation for alpha, the linear expansion coefficient or the length expansion is equals to, we could write down the change of area over to A and change of temperature. What we have to determine the temperature difference, which is this one. So the temperature difference is equals to change of area over 2 alpha into A. Now plug in all this value. So del A is equals to 5 times 10 to the power minus 4 to the value of alpha is equals to 9 into 10 to the power minus 6, and the area is 16 meters square. So the temperature is 17.4 degree Celsius. So this is the final answer. This is the extension of the previous problem. We have to determine the required expansion of the gap. So the previous question, we actually determine the temperature difference. So the first area of this one, where the area was 16 meter square, and here let's say the initial temperature was 0 degree Celsius, and temperature rises up to 80 degrees Celsius. So now temperature rises at 80 degree Celsius. And of course, the material of this sheet, let's say this is lead or whatsoever, doesn't matter. The value of the expansion coefficient is 9 into 10 to the power 6 per Kelvin. The linear expansion coefficient. Uh, the previous one was actually glass. So let's say this is the value for glass of linear expansion, that is 9 into 10 to the power 6 per Kelvin, right? So the temperature difference here actually, del of T is equals to 80 minus 0 degree Celsius. It means 80 degree Celsius. What we have to calculate? Determine required expansion. So we have to calculate the del of A. It means the block within the green dotted line in between the area of 16 meters square and the dotted green line in this black region we have to determine, right? This black area we have to determine, which one drawn right now in white pen. Anyways, del A we have to determine. What is the formula for that? Del of A is equals to 2 alpha A and del of T. 2 times value of alpha 9 into 10 to the power minus 6. Area is 16 and del of T is 80. So we have 0.023 meter square, or let's use more one digit, so 0 meter square. If you convert into centimeter square, you could write down 230 point, actually there is one more digit we could write down. So this is, let's say, 4, and here we could write down meter square. So 2304 centimeter square. In this problem, 2-meter iron rod. So the length of the iron rod is 2 meter initially actually. And in that case, the temperature is 0 degree Celsius. Now, temperature rises up to 10 degrees Celsius. In that case, the green dotted line represents the expansion. So how much the expansion here, del of L, that we have to calculate, as well as for the copper, it was initially 0 degree Celsius and of course 2 meter, and the temperature rises up to 10 degrees Celsius. This amount of length enhanced or expand. So this is, let's say, copper, and let's say here iron, IR. One important data missing for iron, that is the coefficient of linear expansion. So alpha of Fe is equals to 11.6 into 10 to the power minus 6 per Kelvin, and the copper is given here. Anyways, let's determine first the linear expansion for iron. So del of L IR is equals to, the basic formula is, so the fundamental formula is L dot alpha and del T. So let's plug in all the value. So length is 2 meter, alpha is 11.6 into 10 to the power minus 6, and del T is 10 minus 0. So let's put it 10 degrees Celsius. So the final answer will be 2.32 into 10 to the power minus 4 meter, or we can convert into millimeter. So we could write down 0.232 millimeter. A very tiny amount of length will be expand. Anyways, now it's time for copper. So let's write down the basic formula for linear expansion. So subscript CO copper is equals to, of course, the length alpha, the linear expansion coefficient, and the temperature difference. Here only change will be the linear coefficient for copper, and length is 2, and this will be 16.7 into 10 to the power minus 6, and temperature is 10. So we have 3.34 into 10 to the power minus 4 meter. So we could write down 0.334 meter, pardon, millimeter. So the value of copper is compared to more than the iron. And we can make a comment here, like, or maybe a question asked, like, how much percentage of enhancement happen within this two metal or comparison. Indeed, we could comment like 44% more expansion. In this problem, 3 lead sheets in a factory are heated in a different temperatures, right? So all of these 3 are made by lead. An initial area, let's say this is 4 meters square, this is 4 meters square, this is 4 meters square as well. An initial temperature, let's say the initial temperature is 25 degree Celsius, and the first one, let's say heated up to 175 degrees Celsius, which is very important as it's different temperature mentioned in a question. Anyways, this one will be 150, this will be, let's say, 170 degrees Celsius. Now what we have to do, we have to consider, as this is the lead sheets, so the linear expansion alpha is equals to 29 into 10 to the power minus 6 per Kelvin. And we have to compare the difference in mathematically, which we have to compare. We have to compare the area expansion for each of the sheet. So this is the sheet number 1, sheet number 2, and sheet number 3. Indeed, the very first sheet, the area expansion del A1 is equals to the value of alpha, which is 29 into 10 to the power minus 6 into the area 4 and the temperature difference. So before it was 25 degrees Celsius and increase up to 175 degrees Celsius, so it will be 150 degree. So del of A1 is equals to 0.0348 meter square. Now del A2 is equals to, by the way, we have to add a 2 here as well, so it will be 2 times actually. Anyways, now it will be 2 times, of course, 29 into 10 to the power minus 6 into the area 4, and the temperature difference is 135 for the second one anyways. So the value will be 0.0290 meter square. Now it's time for this sheet, del of A3. Same as here, the value will be 229 into 10 to the power minus 6 into the area 4 and the temperature 170 minus 25, it means 145 degrees Celsius. So the result would be 0.0336 meter square. So we have got all the three values. So del of A1 is to del of A2 is to del of A3 is equals to 0.034 0.029.00003.6. By the way, here will be a point. Anyways, now if we divide by 0.029, so we have here 1, of course, and here we have got 1.2 and here 1.16. So the ratio will be this 3. So what actually we can comment after solving this problem, right? So here, when we actually increase the temperature, what will happen? The area expansion, the area expansion is directly proportional to the change of temperature, right? In this problem, copper rod initial length is 100. So initial length L naught is equals to 100 meter, and the this expanded region is 0.02 meter. So altogether actually 100.02 meter. So this is actually the L equals to, I mean the final length, let's say 100.02 meter, and delete this part actually. So this part is actually the increase of length, let's say del of L. Linear coefficient is given, and as this is copper, so let's write down at subscript copper, alpha of copper is equals to 16.7 times 10 to the power minus 6 per Kelvin. What we have to calculate? We have to calculate the temperature, I mean the rise temperature. By using the linear expansion of coefficient, we could write down alpha is equals to del of L over L naught and change of temperature. And here, so what we have to calculate? We have to calculate the rise of temperature, right? So the rise of temperature represents del of T is equals to what? From the formula, we could write down del of T is equals to del of L over L naught times alpha. Let's plug in the value here. So del of L is equals to 0.02. L is 100 times 16.7 times 10 to the power minus 6. So we have got 11.98 degrees Celsius. So we could write down almost 12 degree Celsius of temperature rise to expand from 100 meter to 100.02 meter. The second part of this question, compare the expansion if the same rod were aluminum heated up to 870 degrees Celsius. So here another rod which is made by aluminum, and the temperature rises up to 875 degrees Celsius, as well as determine the aluminum expansion coefficient, the length coefficient actually. So we have to determine the alpha of aluminum. So in this part, the rise of temperature, let's say del T is equals to 875 degrees Celsius, as the initial temperature, let's say it was 0 degrees Celsius, and at 0 degrees Celsius the initial length L naught was same as 100 meter, and the length expansion colored by the green, which is del of L, is equals to 0.02 meter, and to determine the linear coefficient for aluminum is equals to del of L and initial length and the change of temperature. And here the temperature is much higher than the previous rod. For aluminum, it is 875 and L is 100, and this is same as the previous case O2. So we have 2.29 times 10 to the power minus 7 bar Kelvin. So for copper and the aluminium, the length was 100 for both, and the expansion is just about point, let's say, point 0.02 meter for both cases. And for copper, the temperature was 12 degrees Celsius, and for aluminum, it was 875 degrees Celsius. So, what we can comment at last, that copper expands much more degree than the aluminum in case, hence the aluminum needs much higher temperature to rise, right? So this is actually the comments for the argument or the explanation for these questions. Thank you.